Okay, so we've introduced momentum, and we even looked at inelastic collisions. And to be sure, more than 90% of our collisions are going to be inelastic. In fact, pretty close to 100%. In all of our collisions, momentum will be conserved. But there is another kind of collision that we might be interested in, and that is elastic collisions. An elastic collision is a clean one. It is so clean, it doesn't even make a sound. So you just collide, no sound, because there's no energy lost to the surroundings. All the kinetic energy of the collision is conserved. So momentum is conserved and kinetic energy is conserved at the same time. The closest real-world macroscopic example would be a billiard ball collision. Do you have billiard balls? Collision is clean. Actually, truly a billiard ball collision would be inelastic because it actually makes a sound. So a true collision wouldn't even make a sound as the energy is being transferred in a macroscopic sense. Closer to that would be air molecule collisions with the walls. They don't make a sound, and as you get down to the molecular level, then those kind of collisions are indeed elastic. So we have momentum is conserved, so the momentum before equals the momentum afterwards, and kinetic energy is conserved. Kinetic energy before equals the kinetic energy afterwards. So it might look something like this. We have mass times velocity 1 initial, mass 2, velocity 2 initial. They collide and go off after that. Momentum is conserved. Initial momentum equals the final momentum, but kinetic energy is also conserved. So 1/2 mass times velocity squared for both particles initially equals 1/2 mass times velocity squared for both particles afterwards. Well, let's take these two equations and let's manipulate them into one final neat result. Take a look at our momentum conservation, and if I were to put all the mass 1 terms on the left-hand side and all the mass 2 terms on the right-hand side, it'll look like this. And then factor out the mass 1 and mass 2. And so we have this equation, mass 1, V1 initial minus V1 final equals mass 2, V2 final minus V2 initial. We're going to call that equation number 1. Then we'll take kinetic energy conservation, and let's multiply all the way through by 2 to get rid of the 1/2. Put all the mass 1 terms on the left, all the mass 2 terms on the right, and we have this. We're going to have the difference of squares for the velocities on both sides, so let's factor those out for the difference of squares. And I have this, mass 1, V1 initial minus V1 final, times V1 initial plus V1 final equals mass 2, V2 final minus V2 initial times V2 final plus V2 initial. We're going to call that equation number 2. Note that the left-hand side of equation number 1 is also present in the left-hand side of equation number 2. And the right-hand side of equation number 1 is also present in the right-hand side of equation number 2. So if those quantities are equal in equation number 1, they are equal in equation number 2 as well. I could divide equation 2 by equation 1, get rid of the equal quantities, and if I do that, I get this beautiful result. V1 initial plus V1 final equals V2 initial plus V2 final. That is only true for elastic collisions, that the sum of the velocities for one particle before and afterwards equals the sum of the velocities for the other particle before and afterwards. In billiard balls, if you hit straight on, with this coming in with some initial velocity, hits and that goes off, the sum of the velocities of this particle, which final velocity is being 0, so you just have V1 initial, equals the sum of velocities of this particle initial velocity was 0. Final velocity is the same as this coming in. So they just kind of transfer their velocities. This is a really neat equation, but it's probably not quite as useful as the two equations that we're just about to introduce on the next screen. Here's our general formula for elastic collisions. If you know the initial conditions, the masses and the initial velocities, you can find the final velocities from these equations. V1 final is going to equal to mass 1 minus mass 2 over mass 1 plus mass 2, V1 initial plus 2 mass 2 over mass 1 plus mass 2, V2 initial, velocity 2 initial. That is equation number 1. And then V2 final is equal to 2 mass 1 over mass 1 plus mass 2, V1 initial plus mass 2 minus mass 1 over mass 1 plus mass 2, V2 initial. It takes a little bit of algebra to derive these equations. Just have them somewhere handy so that you can use them. Only for elastic collisions. You can't use these equations for inelastic collisions. And we said inelastic collisions are about 99% of our collisions. So you can only use these equations for elastic collisions. But they're kind of neat to use when you can. For the special case where the second particle is at rest, then V2 initial is equal to 0, and only the first term survives in these equations. The second term is lopped off. So V1 final would equal mass 1 minus mass 2 over mass 1 plus mass 2, V1 initial, and V2 final is equal to 2 mass 1 over mass 1 plus mass 2, V1 initial, only if the second particle is at rest. In the case of the billiard balls, V1 final would equal mass 1 minus mass 2, which is 0, times V1 initial, which would be 0. V1 final stops. And V2 final would just equal 2 mass over 2 mass. It would just equal V1 initial. So it works for that case. Let's try it out for this situation. If V2 initial is 0 and a relatively light particle strikes a considerably heavy particle at rest, what's going to happen? Interesting. Let's consider that the heavy particle is infinitely larger than the light particle. So we'll use this, and we're going to say something like this. We're going to have a light particle coming in like this. It's going to hit the large particle. What's going to happen? Mass 2 is infinitely large compared to mass 1. And if that's true, if we look at that first equation, mass 2 is much bigger than mass 1. So in the numerator, we're simply going to have a negative m2. And in the denominator, we're going to have m2. So this is going to be a negative mass 2 over mass 2, or a negative 1, which means V1 final will simply be equal to a negative V1 initial. It's just going to bounce off. So V1 will come in and just bounce off like that. Same magnitude, but just reversing direction. What about V2 final? We're going to have 2 times something really small, which is mass 1, over something really big, which is mass 2, infinitely large. So we're going to have small over infinity, which will be 0. So this will come in, bounce off, and nothing will happen to mass 2. So it's like a wall. Okay. Kind of expected that. What happens though if we reverse this? We're going to have the large particle come in, have an elastic collision with the small particle. What's going to happen? Well, mass 1 now is infinitely large compared to mass 2. In our first equation, we'll have m1 over m1 because m2 is insignificant compared to mass 1. So V1 final will equal V1 initial. V1 comes in, hits this, just keeps on going like nothing happened. Just a flea. What about V2 final? Well, this is interesting. We're going to have 2 times mass 1 over mass 1. 2 times infinity over infinity basically is actually 2. So we're going to have a V2 final that's actually equal to twice V1 initial. How about that? That's unexpected. When this comes in, this will go flying off at twice the velocity of V1 initial. Wow, that's kind of cool. Let's try it out. Set up my chair here. And we're going to bounce this and see what happens when we have close to an elastic collision off this bounce with this basketball here. Let's try that again. It looked pretty good there, but I'm going to try again. Cool. I actually have a device, a toy, if you will, that I bought at the Space and Rocket Center, and it's called the Astro Blaster. Comes with its own goggles, and it's got 4 of these balls set up. And the idea is that with each collision, each successive ball gets twice the velocity of the previous ball. So if you were to take this out to your driveway and bounce this configuration off the driveway, this last ball, the red ball, will go flying. In fact, I've done this. I bought one of these and put the goggles on and went out to my driveway, bounced this configuration on the driveway. The red ball went flying high into the sky, and I could not tell where it went. It went to the neighbor's yard, maybe in the next county, I don't know. Couldn't find it. So I used the extra red ball that they give you and tried that out. Determined to make sure I kept track of where the ball went. Still lost it. Then you use the third red ball, lost that. So within 5 minutes, I lost all 3 red balls. So that's why this one is still in the package, because I know that if I opened it up, the red balls would be gone in no time. I don't see these sold anymore. It might be because they're not really hours of fun, even though they're kind of cool for 5 minutes. Or maybe they've got a few suits based on people poking their eyes out. So I don't know, but I haven't seen them. NASA uses this effect of this 2 velocity elastic collision effect when they send out probes that are destined for the outer solar system. Say if you want to go to Jupiter, you would not just shoot a rocket towards Jupiter because it's just too slow. You need more speed to do that, and we can't really get that kind of rocket power off of the Earth. So what they do is they shoot the rocket not towards Jupiter, but say towards Venus. And it goes and it swings around Venus. Basically that collision is elastic, and it steals the velocity of Venus as it's going speeding around the sun, and gives twice that velocity to the spacecraft. So you shoot it at Venus, whip around Venus, pick up that speed, whip around the Earth again, pick up that speed. You might do that once or twice, and then you shoot out towards the outer solar system with great speed, so you can actually traverse that great distance in a relatively short time, maybe a couple of years, rather than tens or decades of years. So that's a very good technique to get some free energy for these spacecraft. Here's another situation. Let's say you had a metal ball doing an elastic collision with another equally sized metal ball. And let's assume that the collision is pretty close to being elastic. What's going to happen? Well, it's like the billiard ball collision. If they're the same mass, then V1 final will have in the numerator here mass minus mass, which would be 0. V1 final will equal V2 initial will equal 0. And then V2 final will equal 2 times the mass over 2 times the mass. In other words, V2 final will equal V1 initial. So they basically will transfer their speeds. And that's the only way that we can conserve momentum, which is a linear function, mass times velocity, with kinetic energy, which is really based on the velocity squared. So in order to conserve both at the same time, we basically just have to transfer the velocity. Here's the setup. you've probably seen this device. There's a name of this device. You may have heard that it's called Newton's Cradle. But when I bought this at Maury's Gifts at the mall, they had another scientific name for it. They called it Executive Stress Reliever. So that is the technical name for this device, Executive Stress Reliever. And so the idea is, if this mass comes in like this, one mass coming in, to conserve momentum and kinetic energy in the same direction, one mass has to come out. What happens, though, if I come out with two masses? Well, momentum is linear, but kinetic energy goes as the square of the velocity. So in order to conserve both at the same time, if two come out over here, two have to come out over there. That's the only way I can conserve momentum and kinetic energy at the same time. What happens if three were to come out, though? Now I'm going to have three going in and I only have two over here. How can I conserve both momentum and kinetic energy at the same time in what is close to being an elastic collision? Well, if I pull three out this way, three come out on the other side. That's the only way I can conserve both at the same time. And you can tell that this truly is not elastic because you can actually hear the sound of the collision. That was not really good. There we go. A little bit better. So what would happen, and I have to get my money's worth for this because I paid a small fortune for this toy. If I take four out this way, what happens if I take four out and collide with just this one? How can I conserve both momentum and kinetic energy at the same time? If four come out over here, four have to come out over there. What about five? If I take five out over here, oh yeah, five come out over there. Okay. So momentum is conserved, kinetic energy is conserved in both directions. What happens if I pull two out in either end? So I'm going to have a positive momentum in one direction, the equal amount of a negative momentum in the opposite direction. So that total momentum of the system would be zero. So if I pull out two like this and they come in like this, I will conserve zero momentum before and afterwards. But in order to conserve kinetic energy, I must have that the energy movement, energy of motion before, should equal the energy of motion afterwards. So we have, and those are in, kinetic energy is always positive. So whether I have a negative velocity or not, that's going to be a positive quantity for kinetic energy. It can never be negative for kinetic energy. So we must have a finite positive value of kinetic energy after the collision. So we can't just stop. It just can't stop there. We have to go and bounce off. That way the initial kinetic energy equals the final kinetic energy while conserving momentum as being zero all the time. Because these MV in both directions are canceling out. That's about all I can do with this. Buy one of these if you can, or they're great Christmas gifts. If you're going to invest in one, invest in a good one. Don't buy the $7 or $8 one at Walmart. Go out to Scientifics online and buy the $16 one, and you get the larger balls, better strings, and it works a whole lot better. So just a word of advice there. Let's try an elastic collision problem. A 5-gram object moving to the right at 20 centimeters per second makes an elastic head-on collision with a 10-gram object that is initially at rest. Find the velocity of each collision, each object after the collision. Well, if we look at momentum conservation, the initial momentum, which is all with mass 1, since mass 2 is initially at rest, where we have m1 v1 initial is equal to the final momentum, mass 1 v1 final plus mass 2 v2 final. Putting in our numbers, we have 5 grams times V1 initial equals 5 grams V1 final plus 10 grams V2 final. Grams in terms of kilograms here. Let's multiply both sides by 1,000 and divide by 5, and we get V1 initial is equal to V1 final plus 2 V2 final. Alright, we got one equation. But we also know it is an elastic collision. So the sum of the velocities of particle 1 before and afterwards equals the sum of the velocities of particle 2 before and afterwards. This very nice, cute equation. And V2 initial is 0. So solving for V1 initial, we have V1 initial is V2 final minus V1 final. Now we know our V1 initial is 0.2. So we have our two equations, the first one and the second one. And if we were to add these two equations together, straight down, we would get rid of the V1 finals because we have a V1 final plus a negative V1 final. So we end up with 0.4 is equal to 3 times V2 final. Or V2 final is equal to 0.4 divided by 3, or 0.13 meters per second. We can plug this into one of the other equations to get V1 final. V1 final will be V2 final minus 0.2, or negative 0.067 meters per second. So that's how we would solve this, especially if we didn't know those formulas for the final velocities. We would solve it using conservation of momentum and our neat little equation for elastic collisions. We could also use the elastic equations, noting that mass 1 is 5 grams, mass 2 is 10 grams. So 5 minus 10 over 5 plus 10 will give us a negative 5 over 15, or a negative 1/3 times 20. V2 initial is 0, so we have a negative 1/3 of 20, or a negative 6.67 centimeters per second. For V2 final, we have 2 times mass 1 over mass 1 plus mass 2, which will give us 10 over 15, 2/3 times 20. Again, V2 initial is 0. 2/3 of 20 is 13.3 centimeters per second. Same answers, much quickly. So I just kind of did it both ways. The long way, solving two equations with two unknowns, and the short way using our formulas, maybe so you could appreciate the formulas a little bit better, noting that it can make these kinds of problems a whole lot easier. But they're only good for elastic collisions, not inelastic collisions. What is the fraction of the initial kinetic energy transferred to the 10-gram object? Well, our initial energy is 1/2 mass 1, velocity 1 initial squared, and that is 1/2 times 5 grams, 0.2 meters per second squared, or 1 times 10 to the minus 4 joules. Our final kinetic energy of mass 2 is 1/2 mass 2 V2 final squared, 1/2 times 10 grams, 0.133 meters per second squared, 8.84 times 10 to the minus 5 joules. So we transferred a fraction of 8.84 times 10 to the minus 5 over 10 to the minus 4, or 0.884 of the total energy. 88.4% of the energy was transferred from mass 1 to mass 2. Kind of neat. Momentum was conserved as well. What about two-dimensional collisions? Let's say we had a mass coming in, and it's going to have a glancing collision with mass 2 in such a way that the two of them are going to go off at an angle from the initial direction. Mass 1 in this case at an angle theta, mass 2 at an angle phi. To deal with a two-dimensional collision, what we're going to do is treat it as two one-dimensional collisions. In either case, momentum is conserved in the x direction, and momentum is conserved in the y direction. And we'll break it down into simpler one-dimensional equations and then combine the two. So in the x direction, mass times velocity 1 initial in the x direction, whatever that component is, plus mass 2 v2 initial in the x direction, should equal mass 1 v1 final in the x direction plus mass 2 v2 final in the x direction. We take all of our velocities only in the x components and treat our one equation to rule them all, our momentum equation, in the x direction accordingly. Do the same thing for the y direction. The initial momentum should equal the final momentum in the y direction using only y components of velocities. In a special case of an elastic collision where the two masses are actually equal and one mass is initially at rest, if you have a glancing collision in that special case, we would find through geometry and a little bit of algebra, it takes about a page and a half, you can show that the sum of those angles after the collision is equal to 90 degrees. How about that? They will go off from each other at a right angle. You could use this in the game of billiards. If you were to shoot and aim at some point on the other ball, you would know that they'll go glancing off and they'll go off at a 90-degree angle with respect to each other. And you can use that to figure out the angle you need in order to hit the ball into the corner pocket. This could make you some money, so I'm just giving you some physics that can possibly put some money in your pocket, so to speak. Let's look at a two-dimensional problem. A 90 kilogram fullback moving east with a speed of 5 meters per second is tackled by a 95 kilogram opponent running north at 3 meters per second. If the collision is perfectly inelastic, calculate the velocity of the players just after the tackle and the kinetic energy loss as a result of this collision. Can you account for this missing energy? So we have one player moving in one direction, another player moving in another direction, a tackle, so we have a perfectly inelastic collision, and momentum is conserved in either direction, so in the x direction and the y direction. Total momentum will be the vector sum of these two, which will be mass times final velocity in some angular direction. It's perfectly inelastic in x and y directions, so our initial momentum is supplied by player 1 in the x direction. That should equal the final total mass times their final velocity in the x direction. Momentum is conserved in the x direction. So our final x velocity will equal the momentum of player 1 plus divide by the total mass of the system. 90 kilograms times 5 meters per second over 185 kilograms, 2.43 meters per second. In the y direction, only player 2 has momentum initially, and so that momentum should be conserved. Mass 2 v2 initial should equal their total mass times their common final velocity in the y direction. That velocity will be the momentum supplied by player 2 divided by the total mass of the system for this inelastic collision. 95 kilograms times 3 meters per second over 185 kilograms, 1.54 meters per second is their final velocity in the y direction immediately after the collision. So the magnitude of their final velocity, since they're perpendicular, these components, will be, by the Pythagorean theorem, the x velocity squared plus the y velocity squared, square root, which will give us 2.88 meters per second. And the angle that they go off at is the inverse tangent of the y component over the x component. Inverse tangent of 1.54 over 2.43, 32.4 degrees. So if the defensive player can make this calculation before the hit, they can calculate that they can make the stop before the guy crosses the first down marker, and hence get the ball on downs and hopefully win the game. So this is one of the things that the defensive players have to do on the fly. They have to make these calculations in their head while they're playing the football game, or just kind of wing it. Kinetic energy is not conserved in this collision. Our initial kinetic energy is the initial kinetic energy of both masses, 1/2 m1 v1 initial squared plus 1/2 mass 2 v2 initial squared. For player 1, that's 1/2 times 90 kilograms, 5 meters per second squared. For player 2, 1/2, 95 kilograms, 3 meters per second squared. We started with 1,553 joules. Afterwards, they moved together as one mass with one common final velocity. So the final kinetic energy is 1/2 times 185 kilograms, 2.88 meters per second squared, only 767 joules. Where did that energy go? Good question. Half the kinetic energy was lost. The other half is the residual kinetic energy before they finally stop. Well, they're going to heat up because of the collision. There's going to be heat, and there might be some indentation of the pads that might spring back, so that energy could come back. It's definitely going to make a sound when they hit, and that sound's going to take away energy. It could have deformation of the body, broken bones, things like that. Energy has to go somewhere. It's going to go somewhere, and residual. That extra half that's left over is going to be lost to friction while they're sliding on the ground, and that's where that will go after that. So that concludes this lecture in Chapter 9. Our next thing we're going to look at in Chapter 9 is center of mass. So look forward to that